David Smith here with another Flipped Classroom math video. A few tips before we start. Remember that you can slow down or speed up the playback if that helps you follow along. You can also pause the video at any point to catch up with your notes or try the problems before I explain them. Lastly, you could turn on the captions and read my words going along below the bottom of the screen. This lesson covers quadratic functions and their transformations. So we're going to review very quickly the basics of quadratics and then move on into transformations. So first off, a quadratic function has this form: ax squared plus bx plus c, where a, b, and c are constants, are numbers. The only requirement for this to be a quadratic is that the a term isn't 0. There's some number in front of an x squared term. That number could be 1, it could be a fraction, it could be ginormous. We just need a number there. These two terms can be present, but don't have to be. Okay, when you graph a quadratic, it's going to make a parabola. I've drawn a very basic parabola here just to show you the main features. This one opens upward, the limbs go on forever, and it's got a vertex or a turning point where, in this case, it changes from a decreasing function to an increasing function. This is called a minimum. And then we also have this vertical line called the symmetry axis. And every parabola has one of these, and the rightmost limb reflects right across the symmetry axis and lines up perfectly with the leftmost limb. Let's put this on the coordinate plane and take a look. So what I've drawn here is called the parent function, or the mother function, or sometimes I just like to call it the mother parabola. This is the function f of x equals x squared. This is the most basic quadratic function, and it makes this graph here, which I'll go over in just a second. I notice how I label my coordinate axes, and I put tick marks to give you a sense of units. The vertex, or turning point, is at the point 0, 0. So I use notation v for vertex equals 0, 0. The symmetry axis is running right up and down the y-axis. So that is x equals 0. Not anywhere right or left, but at x equals 0. So that's the symmetry axis. Now, this mother parabola has the following features. The next interesting point is over 1, up 1, and then we go over 2, up 4. This is the quadratic function, just squaring our x input. And by the same token, when we go negative 1 and square it, we go up 1, negative 2, we go up 4. So these are very nice reference points to know. You should have this more or less memorized, and my thought is that by the time we're done with this unit, you will have it memorized. All right, here's a key concept. Every change in the quadratic function transforms the graph. So we start with our mother function, and then we do stuff to it to transform it. So I'm going to go ahead and show you some transformations, and then we'll get into the algebra. So the first one, reflection. In this case, we're just reflecting our graph across the x-axis. So instead of pointing upward, now this parabola is pointing downward. Notice how it still has the same vertex at 0, 0, and it still has the same axis of symmetry at x equals 0. So I want to ask you this. What values changed when we reflected it across the x-axis? Pause the video and think about that for a minute. Okay, if you notice that the y values changed, you're right. The x values are still the same, but the y values have gone negative. So now instead of going above the x-axis, it's going below. So that's the y values. Transformation type 2. We have a stretch, also called compression. So what we've done here, here's our mother parabola, the y equals x squared, and we've compressed it in or stretched it up. So the parabola now is still facing upward. It still has the same vertex and axis of symmetry, but now it's squeezed in, it's compressed, so it's rising faster. So pause the video and answer this question. What values have changed? It's the same. For the same x, we now have an increased y value. So the y values have changed. All right, let's talk about the last one here. These are transformations of a type called translations. So translation, you have a horizontal, can slide back and forth on the x-axis, and then we have a vertical. It can go up and down on the y-axis. So this is the third type. It's a translation. Another word for that is a slide. I have seen that before. So there you go. All right, let's get into the math of this. Let's take a look at some actual functions. So what I'm going to have you do is graph these things on your GDC and then come back to the video lesson and compare your results. I'm going to do everything here on the board with hand graphs, but you should be practicing this in your graphing display calculator. So f of x is x squared. So here's my f of x. Now I want you to put that in your calculator and then also do negative x squared and come back. All right, let's see how you did. So I added this. This is f of x equals x squared, so that we know what that function is. And when I put that in my calculator, I get a graph that does the same thing. It just goes down. It's a reflection across the x-axis. So that should tell you something about our standard form. Remember, this is a x squared plus bx plus c. This is f of x equals. That's our general form. So we just played around with the value of a. So what does a do in this case? Pause the video and think about that. So negative a makes the parabola open down. So whatever else a is, in this case, a is just -1, it makes the parabola open down. Okay, so there you have it. That's part of what a does. A is the most complicated of these constants. Okay, next one. I want you to graph, leave your f of x squared on your calculator, get rid of the negative x squared, and I want you to instead add 2x squared to your graph on your calculator. Sketch that graph and then come back. All right, here's what I get from my calculator. I graphed my 2x squared, and this really makes sense. The mother parabola goes through the point 1, 1, because 1 squared is 1. The graph of 2x squared just takes that 1 squared, which stays 1, and multiplies it by 2. So this first point is 1, 2, like that. 1, 2, and this point there is -1, 2. So pretty much we've just taken that and we've compressed it or stretched it. So this transformation is a stretch. So pause the video for a second and tell me what's going on here with what A is doing. Okay, so A also controls the compression factor of a parabola. So A controls compression or stretch. So while we're here, I want you to go ahead and graph one more function. Let's do f of x equals 1/2 x squared. So pause the video and put that in your calculator, sketch it on your page, and come back here. All right, let's see how you did. What I did is I graphed my third parabola, and notice how that one got stretched out, because the 1/2 takes the x squared value, whatever you do when you square your x term, and cuts it in half. So when I plug 1 into my function, I only get 1/2 for my first point. When I plug 2 in for my function, I get squared makes 4, but times 1/2 brings that back down to 2. So 2 is my next point, and so on. So when I have a value for a that's between -1 and 1, I'm going to have a stretched out parabola. So let's talk about what that shows you. The multiplier here determines how fast your y value rises. So when the y value rises really quickly, this number is getting bigger and bigger and bigger. When the y value is between -1 and +1, or when the a value is between -1 and +1, the y value rises much more slowly. All right, let's do another one. Now I'm giving you a parabola in our standard form. Here's our mother parabola. Threw it on my graph. Now I want you to do that in your GDC with this parabola. That is a quadratic function. It's got a squared on it. It's just in a slightly different form. It's in a factored versus an expanded form, but you can enter that into your GDC and graph it all day long. All right, let's see how you did. When I put this into my calculator, what happens is the graph shifts over 3 units to the left. So this is a horizontal translation, And it's a little bit tricky. This number is a plus, but it shifts it in the negative direction. You just have to remember that. It's a tricky thing. People tend to, when they see plus there, they tend to shift it in the positive direction to the right. You have to remember that it goes to the left. One more transformation. Check this one out. F of x equals x squared. It's on my graph just like before. Go ahead and back out that old function, the x plus 3 squared, because now what you're going to do is you're going to graph this one with x squared plus 3. Notice how the plus 3 is outside of the squared. So check that out. Go ahead and put that on your calculator, sketch the graph, and come back. All right, in my calculator, this is what I get. It just shifted the parabola up 3 units. It was a vertical translation of 3 units. Notice how it shifted it in the positive direction, and that plus is positive. So unlike the horizontal translation, this one is what the sign tells you that it is. Okay, one last board in this transformation of quadratics lesson. So what I've done here is I've put our mother function, f of x equals x squared, on a coordinate grid, and we're going to put 3 more functions right on here. We're going to play around with what we just learned about all the different transformations of quadratics. So we've got these 3 more to add there. What I want you to do right now is pause the video and let's put the graph for b, g of x equals x plus 3 squared minus 2. Use everything you've learned so far and put that on your graph. If you have a different color pen, use it. Okay, let's see how you did. So when I look at this equation, I notice that my vertex is going to be at minus 3. Remember, change this sign, minus 3, minus 2. So I graphed that point. I noticed that the a term is positive 1. We don't write it, but it's there. So positive means it opens up. 1 means that it has the same shape as y equals x squared. So the quickest way to do that is over 1, up 1. Now also recognize, I am not referring to your graphing display calculator in doing this. You need to have this skill. On the final exams in this class, there's a calculator portion and a non-calculator portion. So with the non-calculator portion, you have to be able to make a good hand graph. So you want to practice that. Okay, let's move on to the next one. Why don't you go ahead and pause the video and put h of x equals minus 1 half x squared minus 1 on the coordinate grid. Okay, let's see how you did. Here's my equation. Notice how my x term is just simply squared. So I have no value being added or subtracted to x. So that means that the x-coordinate of the vertex is 0 and is on the y-axis. And indeed, that's where I put my vertex. My y-coordinate is minus 1, so I've gone down negative 1. So there's my vertex. Now I look at my a term. It's negative 1 half. First, negative means that it opens down. Got that. 1 half means that the y value is going to decrease half as fast as it would normally do. So normally we'd be over 2, down 4, but I went over 2 and down 2. That's 1 half of the 4. And there is my downward facing parabola for that function. One more. Let's see you do this one. I didn't make an I of x there. So let's do, this is I of x equals negative 2x squared minus 1. Go ahead and put that on your graph. Okay, let's see how you did. Now this one has the same situation as this. No value being added or subtracted to x, so the x-coordinate of the vertex is 0, and again, same thing, minus 1. So the vertex of this graph is in the same place. It's negative 1, 0. Now, negative 2, negative means it opens down. Now the 2 means it's going to decrease twice as fast as it would normally. So that's how I got these 2 points. I went over 1 instead of down 2, I went down 4 on both sides, and I drew my parabola. Oops! I made a mistake on that last graph. If you didn't catch it, rewind the video right now and go see if you can see what I did wrong, and then come back to this video. Okay, let's see if you figured it out. So what I did was I took that function, I used my the same vertex because that's correct. The vertex is at 0, negative 1. And then my problem was that what I did is I went over 1 and down 4, but really it's just down 2 because of my a term. Negative makes it go down, and it's just twice as fast as it would otherwise be. So that's over 1 down 2 to the point 1 negative 3, and over 1 down 2 to the point negative 1 negative 3. So overall it looked about right, which is why I didn't catch it in the moment. But when I reviewed the video, I noticed, oopsie, made a mistake. So I hope you caught that in the moment. Now that you've finished the video, take a moment to jot down any questions that you have so you can bring them to our next class and get some help. You can also watch the video again to perfect your understanding. If you enjoyed the video, please click the like button down below, and if you'd like to help me grow my YouTube channel, please click subscribe.